still show you some bits of code. Okay, so milliseconds matters. You may have seen that motto on Algolia shirts or on the website. We often say milliseconds matters. It's important. And if you look at the documentations of Algolia, the specs, we consider that a query is slow when it takes more than 50 milliseconds. Okay, and a usual query is supposed to run in a few milliseconds. So that's an important aspect of our search engine, and we want it to be true. So it really matters. It's not just marketing. It's a real stuff that we push behind. So why? First of all, we want search to be reactive. Okay, when you enter your search on a website, we're in 2018. We don't want to wait. Okay, that's the normal stuff. Okay, if you don't get a slow networks, too bad. But otherwise, you don't want to wait for the bad reasons. Another point is that we provide search as you type. This means that while you are typing, we do search with what you have typed so far, and each letter you type is a new search query. So that means that it needs to be fast because you are typing fast. Okay, so it needs to be updated because it needs to traverse the networks, needs to arrive on your browser and to be displayed. So we need to answer quick every queries that arrive because it should be part of a search as you type. And the other point is that the data we are searching is bigger and bigger. Okay, we have the use case of data is bigger. It's something that is different. 6 years ago when Algolia started, things were a little bit different. And every years we get, even if we don't have any new customer, which is not the case. We have a lot of new customers regularly, but even on the regular customers, their amount of data is growing. Okay, so, and these customers have more and more users that want to search. So basically, we need to support more and more queries over time. So performance is important. Okay, so that's the idea. The default is to be fast. There is no other way. So what happens in the engine? If you really care about the underlying algorithms, there's a very nice series of blog posts on the Algolia's blog that you can read that talk about the try, the data structures, the consensus. So if I redo that here, I will spend my time and the time of the other speaker just to re-explain everything. I will basically focus on the state of the engine when I arrive. That is, we get something that works, something that is big now, something like 250,000 lines of C++, something like that. So pretty big project. And we want it to stay fast and to be faster if it's possible. So first of all, what is the cost of a query? When you get a query, first of all, you get all the part that is not on our side. Well, not completely. Okay, you're on your browser, you type your query. First of all, you will request an access to an Algolia server, so there is a DNS request. Okay, then you get all the networks exchange. It's probably using SSL. If it's not, it's a problem. Okay, so you get also key exchange for the SSL part. Okay, then you get your networks. Then it hits an HTTP server. In our case, it's an Nginx. And finally, we get to the point where we get the query and we need to answer it. So most of our job in the search engine is on that part, the query execution. And then after that, we need to build the result and send it back. We all already pay a lot during the part that are not emphasized here, that is the networks, the SSL part, which means that the remaining amount of time for the query is pretty short. And that's why I said that we get basically a timeout at 50 milliseconds. This means that a query is too long when we hit 50 milliseconds. So we stop gathering results at that point. And if we get no results, there's a problem. Okay. So now that you have some context, what are our problems? So we want to improve performance. Okay. That's the basic stuff that any any software engineer wants to do. Okay, you write code and you want it to be fast, and then you want it to be faster as much as possible. Of course, you want it to be clean, you want it to be correct and stuff like that, but performances is something that you want to improve. But that's not enough. In fact, we are in a state that we get an engine that works, now we got it for not exactly 6 years, but almost 6 years. We introduce a lot of stuff inside, but it works pretty well. The idea is that we add new features. And when adding new features, these new features should go fast too. Okay? So we need to be sure that any new code is as fast as the previous one. And we also need to be sure that we don't break the other codes. That's something that's easy to happen. Okay? You add just another option. It's just a branch in the endpoint handling. Okay, it looks teeny and simple, but the test is not that free. And even if it's just one case out of thousands, the test is run each time a query arrives, and you degrade your performances. So we need to be sure that anything that we add doesn't break anything. And of course, it's a big project. We need to do bug fixes, we need to do refactor, we need to tackle technical depths and stuff like that. And anytime we modify something, we need to be sure that it's run as fast as before. And if it's run faster, that's better. Okay, so that's why we started to implement non-regressions. One of the things when I talked about the cost of a queries is that we cannot just say, okay, I will put some probes or try to see, since we have for most of our customers, we have they use our API clients. We can say, okay, we can have something that sends statistics for us. If the customers agree with that, we can have some stats. But is that not enough? We don't know if we take just the time for the query to execute on the client side. We don't know if that time is due to the networks, if it's due to the domain request, if it's due to the SSL, if it's due to our side. So that's not enough. So what we want to do is something that is, for us, able to tell us where are our perf, and can we do something about that or not. Okay, so what are the issues? So first of all, what can we measure? So as I said, it can be inside the engine, it can be at a lot of places, and we also have to somehow handle the timeouts, because normally on a standard request, standard queries, we have timeouts, and here probably we want to remove the timeouts for performance measurements. We also have problems with times. So anybody that have played a little bit with clocks on operating systems know that there is no such clock as a correct clock. Okay, any clock has issues. So you get some that are respecting the real time. Okay, so it's accurate with the time zone. If it's the case, it's not always the case, but okay. You get some that are just counting the numbers of ticks since the start of the system, which is the one you want probably. You get also clocks that have cost because it requires a system call. Some others doesn't require system calls. So you get a lot of things that you need to look at, and especially you need also to be sure that the accuracy is enough. When you want to measure milliseconds, you want to be sure that the clock is giving you a precision of at least milliseconds. In fact, you want a little bit more. And then you get all the troubles around IOs, networkings, multithreadings, and stuff like that. Because anytime if you just add multithreadings to a project without any interaction with the outside worlds, just the scheduling part of the multithreading, it will completely break your benchmark because you are not sure of what happens. So that's another problem. And finally, the last one, which is basically the hardest one, in fact, is what are the data we can use for that. The trouble is that the queries we run are not our queries. The data on which the query runs are not our data. That are the data of our customers, even if most of them are public in the sense that That's the content of websites. We cannot just say, okay, I take the index of that customers, it looks nice, it's big, and they got a lot of queries. I will record their queries and play with that. Even without the GDPR, we don't want to do that. And probably our customers don't want to do that, and you probably don't want that company like us do that. Okay, so we cannot just pick the data out of customers to play with it. So we basically need to generate it, which is the part of the story. Okay, so that's the problems, and we get also some constraints. And the fact for that tool to be, that regressions tools to be interesting and efficient, what we need is to be integrated in the continuous integrations test suite. So basically, anytime you push some commits on our depot, you get some test that runs and give you some performances test. So that was our goal, and that's almost what happens actually. So it doesn't reject your code yet, because it still gets some tests that are not perfect, but that's what we want. So we need, for that to work, it needs to be fully automated. It needs to be reproducible. That means that any runs with the same code will produce the same kinds of output in terms of times, which is pretty difficult to obtain. If you play with benchmark, you probably know that. It needs to be accurate, of course. And we want it to cover as most as possible. Okay, so how can we do that? So as I said, I won't go deep in the code, and it's not public code, so anyway. So the first things we've done is to basically break everything. So extract the parts that run the queries out of the engine. So we get out of Nginx, get out of all the threading stuff, all the networks, just gets the part that take your queries, run it, output the results. So in order to do that, it seems simple, but in fact we need to refactor a lot of stuff. We need to be sure that we have just a piece of code that do the job, and not something else in between. So it's really a separated part from the code. The idea is that if it's just a separated part, that is, I take the code outside, copy it to another repo, it's not what I want, because I will testing the same code on and on again. The idea is that the code must be architectured in a way that the query execution part can be used outside of the rest of the project. So that is not completely easy to do sometimes. We need to add the relevant timer. So for the records, I put timers everywhere. So as I said in the second part, we use the monotonic clock provided by the POSIX systems, which we are happy to find out that in C++ and modern C++, that clock is used inside the chrono library. So we don't need to have the wrapper. And I measure every query. So I run a lot of queries, and inside that benchmarking tools, any steps of the queries is measured with a precise clock. So we are able to see for each kind of queries which one is slower than another. If we get several runs, we are able to remove outliers, because you don't want to run each query once. You want to run it several times to be sure that the value you obtain is the real time for that queries. So since we split the code, we don't have any more IOs, so we still have IOs, in fact, because the index is in file. So we need to load that file. But we just have the first load, a little bit play with memory to be sure that it's in memory, and then that's it. No networks, no threadings, and in fact I just discard the result because I don't care about the results, I just care about the time. And for the rest, we generate the dataset. So we take some models to generate indexes, and out of these indexes, we generate queries that provide relevant results on these indexes. Okay, so I don't have numbers because it's not really interesting. But I talked about, I think time is running also, about the results we obtain. One of the side effects of we get now tools that run inside the CI. So anytime you push some codes on the Algolia engine, So anytime search engine, search engine engineer, name that, puts some code, it goes through the test, and we are able to detect any regressions. It's interesting because we also now have tools to test hardware. I don't know if you follow how Algolia works, but we get basically 1,800 servers that we run, where we run our engine. It's groups by clusters of 3 servers that handles groups of indices. So it's our own servers. We normally have the same hardware everywhere, or at least we try to be as homogeneous as possible. But as you know, hardware is evolving, and sometimes the processor you used to have is no longer available, so you want to buy a new one. But before that, you need to be sure that you get the same result with that processors, and the same for the memory, the same for the hard drives, the same for the network cards and stuff like that. So we need to test hardware. So we are currently running tests on a lot of new hardwares using the tools we built for the regressions. So not only we get regression tools, but we also get hardware tools. Once also you get that kind of stuff, you are able to use some other tools to track down stuff on your code. For example, you can use perf. So I don't know if you know Linux perf. So it's a tool that basically grab performance counter from the operating system, which are basically also performance counter from the hardware. And out of that, you are able to get statistics or recording of events inside your code, and you are able to link these events with your code. So basically with that, you're able to find out hotspot in your code. That is the piece of code that is executed the most of the time, without the cost of coverage tools or any kind of tool that usually we use extended codes in order to detect that kind of stuff. Here with perf, you can run it on any binaries, provide your kernel, provide the performance counters, of course, and you have the right to access it. But once you get that, you're able to connect events, performance events, and your codes. So of course it will be connected to your low-level codes. So if you don't have any symbols in your binary, you will just have assembly code. Well, that's okay for some of us. We also get to talk only about queries, but we got a builder for indexing, and we want to bench it also. And the idea of generating data for testing queries is that we will, it means that we have data to generate index. So we use these tools to also generate, benchmark the builder. So far, it's not the most accurate one because it's we don't have as much work to do for the builders as we get for the queries, because with a tiny index, you're able to run thousands of queries. But if it's a tiny index, the builder will go fast and you won't have accurate results. And we also, that's a little bit more tricky, but by building and separating codes, we identify problems in our code base, so technical depths mainly, especially in the query executor and the way we get the parameters of the query. And that's basically schedule some new refactor that we need to do. It's not yet done, but we identify some stuff that some other works to do on the engine just with that project. Okay, so things that are not tests. IOs. As I said, I eliminate IOs. So that's something that needs to be benched in a different way. There are some features of the engine that is not yet evaluated. Especially, we get features for which we are not able to generate data yet. Like if you know our features, you probably heard about query rules or the synonyms. So query rules is a kind of pattern matching on queries. Synonyms is obviously synonyms that you can add in your index. It's a little bit more difficult to generate rules because it's structured data, and synonyms because the synonyms need to be relevant with regard to the data inside the index. So it's not yet generated. We also got the whole indexing pipeline. So if you have already seen presentations about the Algolia, we got several steps with consensus between the servers inside clusters. And so that's in parts that need to be evaluated too, and it's a little bit more tricky because evaluating performances of distributed software is not that easy. And our next steps on that part is live performance and observability. That is basically be sure that we are able to detect performance issue on running projects. So quickly the last stuff, because I still want to show codes. Is it readable? Yeah. Because I said that it's a developer journey. Okay, so that's the things we are living with. So let's just take a. So I can't show you a big piece of code of what we really do. So I just pick some piece of C++, and I play a little bit with what can happen with C++. So basically, I get this nice little useless loop that generates a vector containing integer in form of strings. Okay, so it's a vector of strings, and each of these strings represents the index of the current cells. So it's a completely useless stuff. And what I do is basically how you can write it out of the box. You arrive, you make your loop, so you have a loop from 0 to some size. You create your string variables, convert the integer to strings, and push it back to the vector. Looks okay. But as I prefer shorter codes, I wrote another versions by removing the variables and then run some tests. The move one, I will explain it later because it helps to understand what happens. And when you look at the difference of time between copy and move two, you can see that we get 8% difference of speeds. So you remove the variables and you get 8%. Or if you think that adding a variable is clearer, you add your variables and lose 8%. So that's the nice stuff of C++. So, and that's the kind of stuff that you need to face when you are developing in such a programming language. So I will give you the answer, why it's slower or why it's faster. So I don't know if you know C++ a little bit. How many people know C++ here? Okay, good. In C++ we get a stuff called the move semantic. Move means that rather than copying, we try to just move the parts that doesn't need to be preserved. Okay. So here what happens is that it's a move. That's why I have another version here with a move explicit. A move means that we don't copy the text of the string. We just copy the outer part that just say the memory is here and the length is that, and we don't copy the strings. In that versions, here S is a traditional left value, that is the variables. Okay, so it can't be moved. And here it's a plain copy. And the cost of the plain copy, repeated to power 24 times, is 8%. And that's the kind of stuff that you have to face when you implement a search engine is a low-level programming language. Okay, thank you. So, if you get questions, wait for the catch box. Does it work?
Hello, hello. Okay. So for the data you're generating. For the data you're generating to drive your benchmarks, how are you? What do you do to gain confidence that the generated data is actually corresponds to what your customers? It's close enough to your customers' workloads that it's useful to you.
So we basically take a different approach because the generator of data was used also for the traditional test of the code. So we want something that generates almost all use cases. So we use basic stuff to generate strings because it's text, and then we structure it with. So we have a relatively flat model. So we add some random fields and then random content in the fields and reproduce the schema of each of these records all along in each indices. So it's not the perfect generations, but at least when we test with the coverage, it goes through all parts of the engine. So that's not the best data generator, but it was available.
Okay, I think we might be out of time for questions. I'm sorry, but
That was too long.
Thank you so much, Marwan. That was great. Round of applause. Okay, so next up, we have Maxime. He's a front-end developer at Google. In particular, he focuses on the Google Arts and Code application. And he's here today to talk more on the front end about how you can make your animations more smoother and performant. And his fun fact was that he doesn't look like a normal developer. So round of applause for Maxime.
Is it better? Yeah, okay, it's better. Okay, who's a front-end developer? Okay, cool, that's fine. Who is working on the UI and animation on a web app or website? Okay, a bit less. And who knows what is request animation frame and kneading? Oh, okay, still a lot, that's cool. Okay, so today we'll talk about animations, and I've tried to do something not only for front-end developers, but for everybody. So if you want to animate something, you'll be able to do it. First, I just want to introduce myself by two things. Who I was before, because that's who I am now. So right now, I'm working for 2 years now at the Google Arts and Culture team in Rue de Londres, next to here, this office. Working on the UI and the animation of the app. And before, I was working in agencies and studios on websites, and the aim was to do a website in a month or two, launch it, and never touch the code anymore. So it was cool because we could work for a lot of different clients, but at the same time, when you really wanted to finish something, you couldn't really. And that's why now I'm at Google. It's because you do something and you really, really want to finish it to make it perfect, at least for the user. So what we have is 4 different things. We have one website for desktop, one for mobile, one Android app, and one iOS app. And the cool thing is that on mobile and the Android app and the iOS app, we use web views. So we use the same code for every platform. So it means that every time we push a feature, the feature is pushed for everybody, and we don't have to wait for the mobile team, for example, to do it also on their platform. And I will introduce 2 features I worked on for the past few months, which is inpainting and slideshows. So right now, it doesn't say a lot to you, but I will just explain it to you. First thing is the gigapixels images. So I will just introduce this thing and another old features we have for you to better understand why we did the inpainting and the slideshows. So gigapixels images are super high-res images that we provide. So we have hundreds of paintings, and we can really, really zoom inside the painting. And you can get so close that you can see details that you cannot even see with your own eyes because you just cannot do the focus on it, or because you cannot approach the painting. This is done by this camera, which is the art camera. So it's not the topic, but it's a cool camera. And so here, for example, you have an example of the details you can see, and sometimes you can see some hidden things like this thing that you cannot even see in the painting because you have like the whole painting and you cannot focus on one thing. And that's what we wanted to focus on within painting. And we also have a lot of stories. So we provide a storytelling platform to our partners. A partner is a museum we are working with. So we have more than 1,500 museums around the world we are working with. And they are creating stories like this. So we have thousands of them where they just tell a story. And a few years ago, so I wasn't there at this time, But we did the first in painting, which is this one. Not this one, but that's an example. Where you have a professional creator which talk about one specific painting, and he will take a detail, explain what is the detail, and then jump to another detail again and again. This is what is an in-painting. But on mobile, and it was a few years ago, so you have to think about it, it wasn't possible to do it just for performance reasons. So the simplest solution was to have the detail, so still zoomed, the text again and again. But for the user, it wasn't really that great because it's not really interactive and it's really hard to keep focus on the whole painting. So users weren't really happy. So we've tried to, and we looked at a way of doing it first on mobile because we knew that it was already working on desktop, and using the scroll. So no tap, nothing, you just scroll like everybody is doing, and you see it. And luckily, a few weeks before we introduced the parallax, so I know it's almost everywhere now, but in big companies sometimes it's really hard to do because it has to be really performant. So we worked on it, we launched it, and it was a few weeks before we started to work on the in-painting and the slideshows. So for people who don't know what is a parallax, it's when different elements are moving at a different speed. And here it's depending on the scroll position. So on this example, it was on the previous homepage. You can see that the background and the logo and the text are moving slower than the scroll speed. And this is in painting on mobile that we have right now. So we have so the big picture scrolling up with a scroll. Then this picture is fixed at the top of the screen, so it's immersive, it's full screen, and you really can see the painting. And we have a small animation. So as you can see, we don't really see it because it's a little bit detailed, but when you scroll, you have fading of the picture and the borders on the side. So here everything is white, so you won't really see it, but you can download the app or go on the website and see it. But the borders are reducing, so we can show to the user that the user is entering inside the interactive mode. And then every time we have a caption describing a detail, we can jump to the next detail we want to highlight. And we also do something when the caption arrives at the top. Instead of showing it and hide the detail behind, we just show it, we just hide it, sorry, like here, in like 2 seconds, one, here, now. So even if the user is scrolling up, we can still see the detail in total without any interference. And we also use kind of the same principle with a gyroscope. So when you long press on the in-painting, you have a small animation. And then you just zoom in again inside the detail, and when you move your phone, you can look around the detail. So let's show you now some code. So here, everything is based on the scroll of the user. So we just listen to the scroll, and we will do something which is use the request animation frame function. So it's a tool provided by the browsers to animate things at 60 frames per second in the browser, which is really cool. So it's used like this. So when you call it, you have to call a function. And inside the function, you again have to call the request animation frame, calling again this function. So then you'll end up in a loop, and you will run 60 FPS. And inside the move pixel thing, you will do all the animations you want when the user is scrolling. The thing is, when the user will scroll, we will always call this request animation frame function. So we want to call it only one time. So for this, we just use a Boolean. When we call the move pixels function, it means that we are in the request animation frame loop. And when we scroll again, we just don't call it anymore because it's already running. But it means that now it will run all the time. So what we'll see after. Next thing is to do what we call sneezing animation. So kneading is when you want something to be kind of smooth, if we want to simplify it. And it's really simple. You take one element, this element has a position, and in the future this element will have another position. And we just take the difference between the two positions, and we multiply this this difference by a number between 0 and 1, and we add it to the east position. So like this, it's not really clear, but it's just a magic formula I learned like 5 years ago, and since now I use it almost every day. So the value 0.9, if it's closest to 0, your animation will be really, really slow. And if it's close to 1, the animation will be fast. So when you scroll, for example, if it's 0.9, your element moving with the scroll will be at least almost at the same time, at the same speed, sorry, than the scroll. But if it's 0.1, then it will be really slow. So if you scroll like this, then your element will come after. Next, okay. Sorry. And here the issue, so like I said, we don't want it to happen all the time, because sometimes the user will focus on something and won't scroll anymore, so we don't want calculation of nothing. So what we will do is to check the difference between the current position of the element and the destination position. And if this difference is lower than, here it's 0.1, but it can be 1. If it's inferior to this value, then we say that the current position is equal to the destination position, so you are at the end of the animation, and then we stop everything. So we stop the animation because it's just useless to calculate subpixels, because you just don't see them. And we also stop the request animation frame because we don't use it anymore. And at the top of the move pixels function, you see that we put the is running at false. So the next time the user will scroll again, then we'll run again in the move pixel thing. And at the bottom of the function, you can see element.css transform. So we just change the Y position of the element, and here you can do whatever you want. So you can rotate your element, you can scale it, you can move it, you can do just whatever you want. You can also use a canvas, you can use WebGL, you can do a lot of things. So you just replace this line but by everything you want to animate, and it will work. Now we'll talk about slideshows, where we use the same principle, but we had another issue, which was also, so in painting you have one big image, you have captions scrolling at the same time, and that's it. So we can just fix the image, and just let the captions scroll on top of the image. But for slideshows, which is this thing, we have images overlapping each other, and we have a scale animation, we have a text on the side scrolling, we have the image staying in the middle of the screen with just a small translate, sorry. And so we have this on desktop because desktop are powerful, but on mobile, it's not really great performance-wise, and we cannot really do wherever you want. So here on desktop, for example, you see that everything is done at the same time than the scroll position. And on mobile, you can see that the scale is done only at one moment when you scroll. So if you remember the previous move pixels function, instead of moving an element, you can just add a class, do the animation in CSS, and then the trick is done, and it looks almost the same. And there's also something to consider. It's that, and you really, really see it on mobile, less on desktop, it's that when you scroll, the browser will try to send you the scroll position at the same frame than where you're at, but most of the time it will be sent at the next frame. It means that when you will animate depending on the past and not on your current position. So everything will be laggy, because when you will scroll, you will have an element, and then you will scroll, and then the element will move, which is not nice. And we just used something we haven't really thought at the beginning, which is a sticky position in CSS. And that's what allowed us to do these overlapping images on mobile and on desktop at 60 FPS. This is a definition of MDN. It's not really clear even when you read it like 100 times, but I'll try to make it simpler. So when you have an element and you have a parent of this element, the child will stay inside the viewport until the parent is leaving the viewport. It will be better with an example. But I'll show you some code before. So here we have our 3 slides. So let's say we have each slide which take the whole size of the viewport, and symbolized by a form here, we have the background. So we'll stay simple here, but then it can be complicated. So just basic CSS. So for the screen, so which is a slide, we take the height of the viewport and the width of the viewport, and same for the background, and then it's just to make it full screen. Next thing is to use the sticky position. So here what you will do is put the sticky position on the background, because that's the element we want to see at the screen when we are scrolling. And we'll do something which is, and there's an error. So here we take every screens except the first one, and we give 2 times the height of the viewport instead of 1. But we don't do it, no, we do it on the screen, sorry. So it's fine. And we do a margin top, which is minus the height of the viewport, which means that every screen will overlap the previous one. But the issue is that because in CSS the elements coming after will be on top of the others, then the next slides will be on top of the first one, which is not what we want. So we just do a quick JavaScript thing, which is giving a z-index superior to the last slide. So here, if we have 3 slides, the third slide will have the z-index at 3, the second one at 2, and the first one at 1. Oh, it's the opposite. The first one at 3, sorry. The second one at 2, and the last one at 1. So every previous slide will be on top of the next one. And we have this thing. So we have the background staying at the screen while the parent is scrolling up, which is pretty cool. And if you combine this thing to the thing we did on the in-painting with the easing and everything, then you can do what we've done for the slideshows, which means a lot of small animation to help the user to have an interactive experience at 60 FPS in the browser, which is cool. I've put 2 links, one for an in-painting, one in a slideshow. They will be in the slides, they will be in the video. You can take pictures now if you want. That's fine. You're good? Okay. And that's it. Thank you. And yeah, if you
Thanks. So I think we have time for one question. Does anybody have a question?
Hello.
Hello.
Thank you for the keynote. Do you use React in your website?
Question is, do we use React? No. We use it's Google frameworks. So it's it's for the mobile thing, right? No, for the mobile it's just a
For
mobile.
both.
Sorry.
For both.
For both, yeah. No, we just use the same framework, and we just use web views. So it's not working as React. It's working kind of like Angular, but it's not Angular. It's something internal. I cannot really say more about it because it's internal. Sorry,
Okay.
but no, it's not React.
And what do you think about React as a performance point of view?
I've never used it because that's the thing also at Google. So I've been at Google for 2 years, and when you're at Google, I mean, at least for my case, everything is inside. So when you need a tool, someone at Google did a tool for it. So you can be curious and do other things, but I didn't really have a side project where I needed React, so I cannot really tell you about it. But it looks nice, and now it's true. Like even that's bad thing. and nice things. So it depends on your purpose.
Okay, thank you.
You're welcome.
Maybe just one more question, if anybody has a question. Nope? Okay, you're
Don't be shy.
dismissed. Thank you
Thank
so
you.
much. Okay, so next up, we're going to have Felix. He'll be speaking about performance in Rust. Fun fact about him, he is the owner and operator of the Rust meetup in Paris. So I'm sure he'd be keen to speak to you about that. What else can I say to fill time? Does anybody know Rust? Who actually knows what Rust is? Yeah, okay. That's a good thing. And it's not a metallic corrosion.
Hello, hello? Okay. Can I say those hands again, people who already know Rust? Oh, you're gonna be super bored. Oh man, okay, all right. Hands up if you know C++, and keep them up. And now, keep them up if you use C++ 14, or 2014, I guess. Okay, just curious. I mostly asked that because I wrote my first Lambda today for this talk for C++ 14. Okay, yeah, the abstract for this talk got sort of, I had to revise it. So I'm sorry if I sold you a bill of goods about WASM and stuff because I didn't have time to implement that as part of my talk. If you have your cell phones, the way I do my talks is all the slides are already online. You can take your cell phone now and take a picture of the bit.ly link at the bottom here. And you may want to because there's links to code as we go. And so if you care to visit the code yourself and go to the playground, you'll be able to do so. So a few more seconds. While I'm on this slide, I tried to compress my talk when I made this, which means I got rid of stuff that I usually always include, like what is Mozilla and why is Mozilla working on Rust. So while I'm on this slide, I work for Mozilla. I'm a research engineer at Mozilla, and Mozilla makes the Firefox web browser. But I know nothing about web development. I found the previous talk fascinating because I know nothing about that sort of stuff. And even though I have to hack with CSS just to make these slides. And Mozilla is doing Rust because it's now has Rust in the Firefox web browser. We're using it to basically make Firefox perform even better and be able to hack faster on Firefox without having to run into C++ issues, which if you're a C++ fan, maybe it has no issues, but we'll talk about that. So what is Rust? Rust is it's a new programming language. We're actually still in our 1.x release, but I think we're going to just be on 1.x forever and ever. It's been out for about 3 years now. We're going to have the 2018 edition out by the end of this year, which is sort of a big deal. But it's more than that. It's got this whole ecosystem with these websites devoted to deploying code and libraries that use Rust, and a whole community that we've built up to welcome people in. And this community is made up of people who come from C++, people who've come from Python, people who've come from Ruby. There's a whole bunch of people all coming together to make this melting pot for this language. It's emphasizing control over your code, being able to get low-level control over all the details, and emphasizing speed, but also emphasizing safety in terms of ensuring that your code doesn't have segmentation faults, but also ensuring that it doesn't have data races. So we care a lot about concurrency. We care about performance, and thus we care about concurrency a heck of a lot, but we also care about safety for concurrent code. And the big point here is that we want to be able to give you the ability to do low-level hacking without having to worry about segmentation faults and without having to worry about data races. And our simple slogan here is hack without fear. So why should you use Rust? Well, as I said, the biggest reasons, I sort of gave this big outline before, but the biggest reasons in my head are safety and parallelism. No segmentation faults, no undefined behavior, no data races. Basically, if you stick to the part of Rust where if you don't type the word unsafe in ever, then you should be fine and you'll never hit any three of these top 3 bullets. But the other thing it enables is various kinds of parallelism. We are a multi-paradigm language that enables all kinds of parallelism. And we'll talk a little bit about some of those in this talk. But this is a performance meetup, and so I thought I'd jump straight into performance issues with a demo that if a lot of you have seen my previous talks, you've probably seen this demo already. This top part is Rust code. This bottom part is C++ code. They're pretty similar, actually, at least for something this small and simple. All this function is doing is adding all of the even numbers within a given integer range. And it's doing it with a simple for loop, and it's just looking at each one saying, are you even, by doing a modulo with 2. And if it's even, then it just adds it to an accumulated value and then returns it. Why did I do this function this way and not just a simple for loop? Because I found that the compiler always reduced it to a closed form solution when I used a for loop that didn't filter out the odd numbers. So that's why we're using this very strange function here. OK, now let's jump into parallelism, because that's what I want to benchmark here in terms of performance. So here's some code that's perhaps parallel, and it's perhaps implemented in Rust. I've included the link to the playpen. So Rust has this online playpen. So even if you don't have Rust installed yourself, you can go to this playpen and then go ahead and run the code. But I'm not going to do that because that would give away the punchline. So instead, this is the code here. And what it's doing is it's going to create a collection of threads in a vector. And then it's going to keep the result that it's setting the result to 0. That's going to keep track of as it runs. And it starts off going from start to max. It figures out how much work to put on each thread, this strange increment calculation where it's basically saying, look, there's some value each. That's how much work we want to put on each thread. But we want to make sure that actually each plus val doesn't go over the final threshold value that we're trying to get to. So it first checks that to figure out what the actual increment should be. And then it calls off to that do partial sum function I mentioned earlier. But now it's spawning off a thread to do that work. So the only interesting thing here, perhaps, is that middle part, that middle line, where it does thread spawn, and it has a closure expression. So if you don't know Rust, then those 2 vertical bars there introduces it's a lambda expression. So if you know C++, just imagine I have a pair of square brackets and a pair of parens there instead of the 2 vertical bars. In any case, it's spawning off a thread that just does the partial sum and stores the value in the result. And then after it spawns up that thread, it increments the start so that the next thread that gets spawned will have an updated start value. After it spawns off all the threads, it waits for all of them and then reports its result. So the main reason I wrote the code like this is because I wanted to make it look as close as possible to what the C++ code looks like. Because I wanted to show you that so we could compare the two and benchmark the two together. So this is the C++ code. If you know C++, you might or might not agree with how I've written this. Like I said, this is my first lambda expression was in this slide. It was great because I got to make this code so much smaller than it was before. But it's the same thing over again. We have a vector of threads. We spawn off each one, keeping track of where we want to start and how much work to do in the thread. But it's the same thing where we're just spawning off that thread that's going to do the partial sum and accumulate the result. After we spawn off all the threads, we wait for all of them to report the result. OK, so let's try the C++ code. Let's get some timings. So we run. And I'm a good programmer, so I print out the actual result you computed each time. So I did 4 runs and got the timings. And it's an average of 1 second on my laptop, about 1 second. OK, so what happens when you use 4 threads instead of 1 thread? Well, when you do that, same result. That's good. And it's about a quarter of the time, a little bit more than a quarter of the time. But it's still pretty close. That's great. That means you get C++, we're getting a good amount of speed up per thread. But just to be sure that I couldn't maybe get some more speed up on this laptop, I went to 1,000 threads. Let's see if we get more speed up that way. And the answer here is, nope, you don't get more speed up, but we do get something. We get an invalid result, which means that all of these numbers are bogus because my code doesn't work. My code is broken, so we shouldn't be reporting these timings at all. And what's the problem? The problem is there's a data race. There was a data race in my C++ code. When I showed you that closure expression, there was a little hidden ampersand there that I needed to have because that's the way to say, look, when you have free variables in here, I want them actually to be treated as things I'm referencing by reference so that I can actually do an update of them in this thing where I'm doing result plus equals there to accumulate the values I'm getting. So this is a data race. Each thread is going to be racing to read from and write to that result variable. And that's the very definition of a data race. And so you get undefined behavior. And so what about the Rust version? I made all these claims earlier that you can't have data races. So I basically showed exactly the same code for Rust. What happens here? The answer is that this code does not compile. And thus, we don't have timings for it because the code does not compile. Instead, with Rust 2015, you get this error message that says, you can't do this code the way you wrote it because you're spawning off this thread that has a closure. And that closure might outlive the value you're borrowing. You're borrowing this result value implicitly. And it might outlive it, and so that's not going to work. So what's the issue here? Well, OK. Oh, wait, one more thing about that version, though. It does suggest something. It says, if you use the move keyword before the closure, that'll change things so that you get transfer of ownership. So The next version we try, I'm a person who's all about compiler. When the compiler gives me a suggestion, I just dive right in. Let's try using that suggestion, see if it fixes everything. So this is version 1, because our array indexes start at 0, so the previous thing was version 0. So let's try doing exactly that thing. OK, the great thing is that this code compiles. All I did was add that move keyword, and it compiles now. So we can go to the playpen and run it, but I'll just go ahead and show you what happens. 4 runs, 1 thread. What are the timings we get? Oh, shoot. So what went wrong here? So obviously something's terribly wrong here because the results are definitely wrong. And what's the problem? Well, the joke here is that there's this phenomenon that people often refer to with these strongly typed languages like ML and Haskell and Rust too. This phenomenon of, once I finish wrestling with the compiler, the code magically always works. Isn't it great? But that didn't happen to us this time. So yeah, Rust is not going to prove your code correct. Sorry. But what did go wrong here? The issue is that move keyword we added meant that we were making copies of the values that we had referred to in our free variables. The free variables of this lambda expression are the start integer, the increment amount, incr, and result as well. So we're putting a local copy of result into that lambda expression, which then gets updated locally, which is great for that lambda expression, great for that closure, but the original code, the original result that we are trying to accumulate into doesn't get updated at all. So that's the problem here. That's the problem with v1. So that's the sort of way I'm going to introduce ownership, is by talking about that example, is that is this idea of ownership where in Rust you have a notion that every value that's somewhere has an owner. Some of them might be values that can be copied freely. Those integers I talked about could be copied freely between entities, but other things like vectors can't be copied. So here's some examples of Rust types, just to give you an idea of the syntax of the language, a little bit higher level. We have generic types just like C++ and like Haskell and ML and many other modern typed languages. And like C++, we actually implement our generic types by monomorphization. We'll make separate copies of the code for each type that you instantiate at. So that's unlike ML and unlike Haskell. That's because we want to get maximize our efficiency in cases like this. So examples of types are things like vectors or strings. So you saw in the very first talk the example of a string where things are being moved from place to place, and this distinction between copying a string versus moving it. In Rust, everything's move except for really basic data. So vec is move because it's something that allocates storage. That's this thing you're putting stuff into, the representation of the collection. And likewise, a string is something that's moved. It allocates a buffer and has the buffer of characters. And when you transfer from place to place, it gets moved. It keeps ownership of that buffer as you go. But then there's things that are copyable. 32-bit integers, they're copyable. They can be freely copied. Characters, Unicode characters, they're freely copyable. And then there's these interesting cases like arrays, where if you have an array of copyable things, that's what the syntax here is for this square brackets thing. That's a length n array of t's. If the t is copy, then that array is copy. And this is a tuple over here, a tuple of 3 parts. If those 3 t's are copyable, then the whole tuple is copyable. Okay, this idea of ownership is really important in Rust. It enables a number of things. It enables us to use RAII style destructors. It enables us to ensure there's no dangling pointers, and actually is the basis for us to ensure there's no data races, which, these are all great things for removing large classes of bugs that encounter real code in practice. And the way I sort of like to summarize this is that there's a question that it forces you to ask whenever you're designing an API. It forces you to ask yourself, hey, when I'm transferring this value in, do I need to actually take ownership? Do I need to actually take that on myself and then be responsible for cleaning up after this data type? Or would it suffice just to have temporary access to the data? I don't actually need ownership of it myself. And the interesting part, I think, about this question is that I think good developers already ask this in any language in practice if they care about performance. It's just that in Rust, you're forced to actually encode it explicitly as part of the function signature. And we check it. OK, so there's more Rust types. In particular, we let you have references to data. There's 2 kinds of references, ampersand mut t and ampersand t. There's also unsafe pointers, which are star t. That's more like the kind of pointer you have in C and C++. Plus, there's a whole bunch of library reference types, box, cow, RC, others. We aren't going to need to talk about those today. So with that in mind, that's enough to move us to version 2 of our program. So here, we're going to do the same thing we did with version 1 in terms of using a move closure. But now we're going to try to actually borrow that result pointer. So we're going to borrow a pointer result and then move that into the closures. So this way, we avoid moving result into each closure because that was what caused us to fail to actually update the thing that we want to update. Here instead, we're going to borrow result and then move that borrow into the closure. When you try to do this, you would then get a compiler error. In this case, we get the error, at least in Rust 2015, that the result does not live long enough. You're attempting to make this borrow of something, and it's warning you ahead of time. That result is stack allocated, and yet you're passing it to a thread that has to live for the static lifetime. So borrows can't outlive borrows can't outlive the owners of their values that they're borrowing. And this thread spawn function creates a thread that can outlive the stack frame. More generally, it can outlive the whole thread that has spawned it. And that might lead you to the question, well, does every thread have to do this? Do all threads actually terminate at arbitrary times in the program's lifecycle? And the answer is no. In fact, there's alternative threading APIs that will ensure that your threads follow a tree structure where one thread will spawn up other threads and then they all have to finish before this thread will hand back control in the stack frame. And so in fact, that leads me to then discuss, rather than try to put all possible threading APIs into the standard library, in Rust we have this community that's built up this curated set of crates. Crate is our word in Rust for libraries. So we have this set of crates online called crates.io, and Cargo is our tool for interacting with that system. So when you design code in Rust, you are free to grab code from crates.io and upload your code to crates.io if you want to share your library with the world. And there's two examples of libraries that I'm going to give a special shout out to because they're all about parallelism. There's Rayon, which is designed by Nico Matsakis, who's one of my colleagues at Mozilla, who is actually the technical lead on the Rust project. And this is a library that's focused on work stealing based parallelism. Who here has heard of Silk? C-I-L-K. Anyone? No, that project's pretty dead. Okay. Who here has heard of work stealing? Okay, so work stealing is a method of thread scheduling where the basic idea is that instead of trying to decide ahead of time, hey, let's have 4 threads and distribute all the work evenly amongst them, what you can do instead is say, look, we've got a pool of threads and we got some amount of work, and we're going to start off work on all the threads at once. And then if one thread finishes what it's working on, it can go and try to grab pieces of work from other threads while they're busily trying to do part of the task they're working on. That's the basic idea. Rayon is all about enabling that kind of programming. But another library that I want to mention is Crossbeam. It's another parallelism library that has been developed by Aaron Turon, who's actually the project lead for the Rust project at Mozilla. And he's also a colleague of mine from many, many years ago. So we're going to use Crossbeam to make version 3 because we're going to try to implement this notion of having a relationship between our threads where one parent thread is always going to outlive the threads that it spawns off. We're going to try to make a use of that idea that you don't have to always have your threads dying at arbitrary times. So here's version 3 of our program. And this one, we actually use Crossbeam to create what's called a scope. That's the very first line up here. It creates a scope, and within that scope, we're allowed to refer to things that are outside the scope freely. In particular, we're allowed to refer to that result variable at the very top. The reason this is important is because within the scope, down here, we see the scope spawn. We get to spawn off threads, and we have a guarantee that all the threads that you spawn off within a given scope have to finish before the scope itself, before the closure that we're invoking here at the outermost level returns. I'm explicitly invoking the join method here just for by analogy with my previous slides. But in fact, if I left out these bottom lines here with these joins, the API for Crossbeam would actually enforce that. It would force them all to join itself. So I could have left those lines out and gotten the same behavior here. Okay, the whole point is to ensure that we know that all these threads finish, that we spawned off before we allow you to return from the creation of that scope object, which means that we know these threads can safely reference that result variable that's on the stack frame. So maybe this fixes everything. The answer is no, it doesn't. We still haven't fixed it, and the reason we haven't fixed it is because Rust has another rule. Rust has another rule that says you can't actually borrow something more than once at a time mutably. If you do what's called a shared borrow, where you only have read access, you're free to go ahead and borrow that as many times as you want and have as many aliases as you want. But if you borrow something mutably, there's a rule that says that means that that person that's doing that borrow has exclusive access to the data that's being borrowed. Of special note here, by exclusive access, the borrower here, like result pointer, borrows result mutably. Even the owner of result, while this mutable borrow is around, even the owner of result doesn't have mutable access to it. It's given up the ability to mutate result and handed that capability off to whoever has result pointer. So the reason that we have these multiple reference types between the shared reference ampersand and the mutable reference ampersand mute is to distinguish between these two kinds of access. And this enables us to have safe parallel APIs in Rust. So the basic idea is there's three kinds of types you need to know about. If you just see T by itself, this means ownership. If you transfer a T from one place to another, it means you're transferring ownership. You don't have to say standard move the way we saw in that very first talk. It just happens automatically, which means whatever performance benefits you may or may not expect from that, you get it for free just by moving stuff around. Then there's these other two kinds of types that you see a lot, where you see exclusive access with ampersand mute T, which means I have mutable access. And the reason I'm putting that in quotes there is because it really means you have exclusive access. It's a stronger condition than just being able to mutate. It means that you know no one else is going to be able to get that kind of access either. No one else can read or write it. And then there's this shared access thing, ampersand T, which is read-only. And I have that in quotes too because there's tricks you can use to get the ability to mutate something that's behind an ampersand T. Like you can put in certain types, like an atomic integer that allows you to atomically update something in place. So it's read-only, plus it lets you get mutable access to certain kinds of data types that will be explicit in the source code. But the real point is that it just means it's shared. And the only thing you know when you say ampersand T is that you have read access, and some other people might also have that same ability to access, and you can't predict who they are. So this is me just saying the same thing over again. Exclusive access means you do not allow simultaneous mutable borrows of unsynchronized data. There's like three important words there: simultaneous, mutable, and unsynchronized. Oh, geez. Sorry. That's actually my reminder to telling me that I have to leave to go to a meeting. But I'll try to finish the talk. OK, so this rule is usually enforced in Rust via static analysis in the compiler itself. But also we have some library types that enforce it via dynamic checks within the libraries. So all right, I give you sort of this big picture here of all these problems in the code, and then show this final example that had this issue with attempting to take a mutable borrow and having simultaneous mutable borrows of that same result value. And that was the heart of the problem we saw in C++ as well. And in both these languages, you can eliminate this data race rather easily. The common approach is to actually wrap a mutex around the result. And that way, then, whoever updates it has to first grab the mutex, and that ensures no other thread gets access to it. That's one way to do it, and that's a very common approach. Better still, maybe you could use a special atomic operation. All we're doing is updating a variable, integer value here. It's a 64-bit integer, but if we're on a 64-bit platform, we should be able to do compare and swap, or fetch and add, or some other instruction-level atomic operation that'll ensure that this access is synchronized, the update is synchronized, and that other threads will be forced to sort of coordinate with it properly. And maybe better still than that, we don't need to actually take simultaneous mutable borrows of the same result variable. We're only creating, what, 4 threads, maybe 1,000 threads? Guess what? We could allocate state for each one of those threads and let them write into their final destination for their result when each of them finishes. And then when all threads finish, just sum up those 1,000 values, or 4 values, depending on how many threads you make. So there's lots of ways to solve this problem. And you can do it in C++ and Rust. My point isn't to say you can't express this in C++. You can very cleanly. But we didn't think about it, or at least I didn't think about it when I first wrote the code in C++. Rust forces you to resolve this bug in some way, and C++ doesn't force you. It allows silent, scheduler-dependent failure. You may have noticed we didn't see the bug when we ran with 1 thread or 4 threads. Even when we ran with 1,000 threads, I only saw the bug 1 out of the 4 times that I showed you. Guess what? I had to redo that experiment a couple times to actually see the event occur. So it's something where these bugs are very subtle and hard to predict. So here's version 4 of the code. I actually went back using standard thread spawn here because we actually don't need to use cross-beam scope thread abstraction. It's fine here to use the standard thread because one nice thing about Rust's standard thread API is that each closure for standard thread, it can return a result via the handle that you've created. So here, when we do standard thread spawn, we pass it a closure that returns the result of doing the partial sum. And then that result will be stored in the handle for the thread when the thread returns. And that way, now in this for loop down here is where we actually update the result variable. So now we're in a case where this final loop for the threads, when it joins all the threads, it's actually significant that we look at the value that's returned from the join and stash it away. Before we were just discarding the result of the join because there was no information in it. OK, Okay, so yeah. So in case you're curious, yeah, I did the timings for Rust as well. For some reason, it's slightly faster than C++ code. I can't explain why. So there's other cool stuff in the language that we have to leverage these concepts that I've outlined here. We have set and sync traits. That's the way we actually let user data types encode properties about whether a data type can be sent from one thread to another, or whether a reference to that data can be sent from one thread to another. There's a distinction here that's subtle and worth looking into. We have lifetimes, our way of actually expressing that you have a reference that outlives another reference, or a reference that has to live at least as long as some other piece of data. That's encoded explicitly in Rust via the concept of a lifetime, which I didn't show you any examples of here because I only had very limited time. We allow you to do object orientation. You can write object-oriented code if you want to, but I can't explain how that works. It's different. It's a little different than C++. That's all I'll say. And we have unboxed closures, which or I shouldn't say a lot of languages, but it's unusual to have unboxed closures, I guess. In a language that has closures, usually that means you've garbage collected them in some way, and they're always heap allocated. For us, you can have closures that are stack allocated and ensure that they always finish before they have to return from the stack frame they're allocated on. And we have FFI interop. If you need to interoperate with foreign code, we've got a great interface for that. C++ is the one problem area here because we don't have an ABI that we can guarantee for C++. And I don't know what the plan is personally about this. I should know, but I don't. It's a problem we need to solve. But for now, you have to use C as your base language to interoperate. But a lot of languages resort to C in this case. We have a growing community. I alluded to this before. I've put links to the various conferences that we hold. In particular, RustFest is the EU-based conference that you should look into if you're curious about this. And there's the meetup in Paris. If you actually live here in Paris, we have our Rust Paris meetup. I just recently scheduled, after months of failing to do so, I finally scheduled a meetup for now early November. Who here RSVP'd to the meetup I scheduled yesterday? Okay. Well, I wasn't sure because so many of you said you programmed in Rust already. Doesn't matter. I had to reschedule it because it turned out that the time I chose conflicted with the WebAssembly meetup, and so that was clearly a problem there in terms of an overlap in the communities. Okay. And I want to finally just mention this idea about Rust where, some people thought the project was largely about trying to get C++ programmers to program safely. What we've discovered is a huge part of our community is made up of Rubyists and Pythonistas? I'm not sure, who said, you know what, I was programming these scripting languages, but I wanted to learn more, and this Rust thing seemed cool, and now they've learned so much about systems programming that they got here via Rust. C++ and C scared them. They were worried about the segmentation faults. Rust gave them a path to learn more. And the best way to summarize this is that someone who says programming in Rust has made me look at C++ in a whole new light. That's a nice way of saying I think in horror about all the C++ code I wrote back before I learned Rust. Okay, that's all.
Do you have time to take one question?
Yeah, sure. I mean, I'm already late to this meeting at this point. Sure.
Okay, one question. Who's got a burning question? Oh, you might be saved.
All right.
Okay, well, thanks so much, Felix. That was great. Super quickly before everybody runs away, we are doing a search party next December 6th, and the theme will actually be community show and tell. So if you built any cool projects with Algolia and you want to present them, please let us know. And there's fajitas in the back. Thanks for coming, everybody.